So hello, Kate and Shane and David and Pooja and Kellam. This is our week 5 webinar. So it's actually a really important chapter. I don't know if it's the hardest chapter, but we're going to be using it a lot, and it is the most important result of all of statistics is what we're going to be doing today. It allows us to basically do statistics, and that's called the central limit theorem. I'm also going to chat at the beginning a little bit about the online exam, because I know there's some questions, because I haven't talked too much about it, but there's not too much to say, as you'll see. But that's a plan. It probably won't go that long, but we'll see. I'll always say that. But as always, if you have questions, just let me know. I want to mention that I've started grading the projects. I'm about halfway through. And, you know, some are really good. Some could need some work. Just depends. And I'll be grading it, and I'll finish by the end of the week for sure, maybe tomorrow or the next day. So we'll see. That's my goal. It'd be nice to finish by Thursday. Then I'll have it all in for y'all. So that's the main thing. But I want to talk about the other big thing coming this week. And David, you already mentioned it, and that was the online test. So I thought the best thing is probably to share my desktop. I share the screen so you can see. So let's do that. Okay, so here's the just home screen. And I figured I'll start with the syllabus a little bit to give you some ideas on dates and stuff. If you go to the syllabus, you will see that in terms of the exam, we're in February, and I believe it says it in here. I'm trying to find it, but I know it's in here. Assignments, here we go. So by February 9th at 11:55 p.m., you must complete your online exam that covers chapters 1 through 6. Okay, notice the exam is much larger, and you can only take it once, which means you only get one attempt at each problem. There's no time limit. You can work as long as you want. Obviously, you have to finish by the deadline. But other than that, you can spend time working on it. This is not a proctored test, but you're not supposed to get help either. You should be doing this by yourself. So just a note, and maybe I'll even scroll down and pop it in. I guess I should probably look like a student or it won't work well. I have to go home. And just a second. There it is. Student view. There we go. Then you can see what it's going to look like. Okay, so now if we go to the syllabus, for example, or you go to the module, either way. And we scroll down to this week. You'll see online exam, chapters 1 through 6. And if you click on it, and I start assessment, and this is important to note, notice that there are 50 questions on it. So this is long. This is long, but you only get one shot per question, so it's not like you're going to be spending all day on each question. Some are very quick. But give yourself time. This is pretty much what these come from the question pool from the homework, basically. So that's the important thing, is that you should be able, when I say homework, I mean online assignments, I guess, the computer assignments. So you should be able to do all of those, because you're going to see some of the same ones, actually. Okay, and some will be different. But that's what this online assignment is. And again, do your best on it. Don't wait till the last minute, because there's 50 questions. It does take time. I can't tell you how long it's going to take you, because everyone works at a different rate. But it is something that you need to work on. And again, don't wait till the end. Okay, any questions at all? I purposely don't share answers to the practice test for this practice test, because the idea is on this online assignment, you get to do it, and you don't get to see the answer while you're doing it. So So I don't do that on purpose because then you'll be able to see answers to it. If you want to practice questions and have answers, then go back to your regular homework from chapters 1 through 6. So for example, I don't know, chapter 3 assignment, I think it's that one. And you can click practice, and then you can try some of these. Okay, and those would be more like the real problems. The only difference is if I submit this and I say, no, it's not a probability, that was wrong, it actually, you can find out your right answer. Whereas it's not going to tell you the right answer on these problems, and you don't get to try again. There's no try agains. So that's why this is not a practice test, because these you get to try again. Does that make sense? But if you have any questions about a problem, that I can help you and post on the Q&A, and then I'll answer questions. That I'm willing to do. But I really want the practice test to be a practice test and not just more homework problems. And that's the reason why I did it that way. Okay, any other questions before we move on? Any other questions? Okay, so I want to talk about, the nice thing is I'm going to bring in, I can leave student view here. I want to bring in a nice application. It's one that I have done a lot from. And honestly, this is not teaching or anything, but because of good understanding of this particular application, I have made over $100,000. So not bad, right? And I've been doing it since I was a college student, actually. And then guess how I made that kind of money? No guesses? Yeah. So let me show you. In fact, today was a multi-thousand-dollar day. So here is the latest stock market. And I want to mention something, and I want to talk about a couple things. And we're going to do some comparisons. So one thing is we have a bunch of different things. For example, you have the Dow, you have S&P 500, you have a NASDAQ, global Dow, all kinds of different things. And I'm popping this screen on because with this screen we can actually see the numbers, which is nice. I tend to like Market Watch for that reason, is you can easily see what's going on. And there's others too. And I want to talk about why this particular topic is important in terms of what we're doing this week, which is essential limit theorem. So I think I want to share not this anymore, but I want to mention it. We might go back to it in a bit. And let's do a new share. And I'm going to type some stuff. And this is the biggest theorem of the entire class, but we don't even state theorems too often except now. And let me write it out. It's important enough. I'm going to put it in red. This is called the central limit theorem. Okay, and there's a lot I want to say about it. So I'm going to give myself lots of space. So central limit theorem says the following. First, we're going to be in a certain situation. We're looking at a sample. Consider a sample size. And let's look at all possible samples from a population. So the example I gave is we might want to look at all possible collections of 30 stocks from all of the stock market. Okay, and by the way, there are a lot of stocks out there. Okay, many different companies you can buy stock in. So we're going to look at, say, all samples, maybe even 35 might even be a better number. And what we're going to be looking at is we're going to be looking at the two most important statistics that we can get, that we've talked about already, What are the two most important statistics for our class? Who remembers? I know you all know it. Descriptive. Descriptive is a type of statistic, but I'm looking at a specific example of what one statistic. And it's called the, here's a hint, you had to write a whole paragraph on it in your projects. So standard deviation, good. So standard deviation is one of them. And what's the other really, really important one besides the standard deviation? The one we really focus on. Any ideas? You all know it, I promise. Yeah, the mean. Okay, so I want to write down a few things. Actually, I don't need all this space because we'll write out some more. So I'm going to, now I need to draw because we're drawing in Greek now. So first thing, I just want to remind you of some symbols. What does that symbol mu mean? Yeah, there's a lot of different means though, it turns out. It's the population mean. Any questions on that? Then we also have another symbol, very important. What's that symbol tell you? What does that mean? It's sigma. That's how you read it in Greek, but what does it represent? I'll start it off. Population. Very important.
Isn't that
David,
standard deviation sign?
yeah, standard deviation. Population.
Is that
Any questions on that? All right, that's the population mean and the population standard deviation. We have some more symbols. We have that symbol. What's that one represent? Yeah, that's equal to the sample mean. Okay, and then what about just S? What's that? Yeah, that's the sample standard deviation. Any questions on that so far? Okay, those are the ones we already know, and now I'm going to build some more. So now we're going to say, let's suppose that we look at all possible samples of, say, sample size 30. And each of those samples will have a mean. Do y'all agree? Right? Every sample has a mean. A mean is a number, and each sample will have a different mean. So there's all these different numbers that are sample means. Is that clear? If you have a whole lot of different numbers, you can find the mean of those numbers. And the symbol we're going to use for that mean of all the sample means is mu sub x bar. So that's the population mean of all possible sample means. You see it's starting to get a little weird? And that is called the mean of the sampling distribution. Any questions on that idea? Okay, we could also think about all those different means that we've looked at. There's a mean for every sample, let's say size 30. And if you have a bunch of different numbers, we can find the average of those. That's the mu sub x bar. You could also find the standard deviation of all those. So we could find the standard deviation of all those, and the standard deviation of all those will be sigma sub x bar. Any questions so far? And that is equal to the standard deviation, I'm just going to write SD, of the sampling distribution. And it has another name. It's called the standard error. Any questions about that one? So you see, we're starting to get a lot of symbols, and you need to keep track of them and what they mean and how they differ. So are there any questions about any of these symbols? Okay, so now that we have all these symbols, now we can state the big theorem, the central limit theorem, that puts some of these things together. So I think I'll do it in blue to show that this is a statement. And that is, if we look at mu sub x bar, kind of purple more than blue, mu sub x bar, that is always equal to mu. Any questions on that? So what it says is that if you look at the mean of all possible sample means of the same sample size, that will always just be the mean of the population. Okay, and what that tells us is that because of that, that if you look at a sample mean of a single sample that you do, that will be our best guess for the population mean, even if it's not exactly it, but at least it's not biased. Because again, it's the mean of those types of things is just the population mean. All right, now comes the next one. Now let's look at sigma sub x bar, the standard error. Any guess on what that might equal to? Any guesses? So you can say it or put in your chat box. I don't see y'all typing at once. All right, maybe I'll say it. It turns out it's not sigma. It's better. It's sigma divided by the square root of the sample size. So again, right now it might look like a messy formula, but it's really important to understand what this says. If you have a large sample size, then you have a square root of n on the bottom. So let's say you had a sample size of 100. Well, the square root of 100 is 10. So that means that the standard deviation of the sampling distribution is 1/10 the size of the standard deviation of the population. And that tells you that your sample mean, if you have a large sample, is very likely to be close to the population mean. Because remember, if you have a small standard deviation, then that means that most of the values are going to be close to the mean. And if the mean is the population mean, because sigma sub x bar, mu sub x bar is mu, that means that your sample mean is likely to be close to the population mean too. So that means if you can do a survey and you have a large sample, then your sample mean is likely to tell you the truth about the whole population? Any questions on that? Okay, here comes the next biggie. And that is, let me do it in next. If the sample size, n, is greater than 30, then the sampling distribution is approximately normal. Where have you seen sample size greater than 30 before? When did I make you do that? Yeah, the project. So the reason why I told you you had to have a sample size greater than 30 was if you do, then you understand the data better because the sampling distribution is normal. And if you know it's normal, then you can use chapter 6 and you can do your normal CDF and find probabilities. Does that make sense? So that's really important because if you don't know what the sampling distribution is, then you can't find probabilities. And you don't understand much of anything. So this is a big, big theorem. Okay? It turns out, I'm not going to write this down, but it's somewhat important, that if the distribution itself was normal, then you stay normal, even if your sample size is small. But if your sample size is large, you don't even have to worry about the distribution. You always get a normal sampling distribution. Okay, any questions on that? Okay, so this is a central limit theorem for means. So now let's use it and let's talk about it. So I'm going to need to erase this. So hopefully you guys have all this idea. Maybe I'll keep the blue part because that's the important stuff. Let's go to... Okay, so now let's talk about the stock market. Okay, and I want to talk about a little bit of investing ideas. Okay, first thing is that if you look at stocks, you look over the last 20 or 30 years or so, any guess on the average return for any individual stock? If you look at all the stocks and find the average of the population mean of the stocks, anyone have any idea what that return is? What percent return you get? Okay, 12% is a little longer actually. If you go 20 years, it's about 9%. If you go 40 years, it's about 12%. But we could use 12%, that's fine. Okay, now here's a harder question. What do you think the standard deviation is? Because remember, stocks don't always go up, and they don't always go up by exactly 12%. What do you think the standard deviation is for stocks? Any guess, even if it's an estimate? Okay, it's a lot more than 3%. Okay, it's a whole lot more than 3%. Because stocks go up and down. If it was standard deviation 3%, almost just about all of them would go up. Does that make sense? Yeah, 24% is probably a better estimate. Does that make sense, Mark? So now I have a question. Now let's pop it in. Not that one yet. Oh, you know what? You can't see this. I just realized that. I was showing you the stock market. You're still seeing that, which is good because I was about to go back to it. Okay, so here's the question that we got to do. So the first question, it's a two-part question. So the first is if you invest in a single stock, what is the probability of losing money. And again, we're going to use that the mean is 12%, standard deviation is 24%, and we need to assume the distribution is normal. Otherwise, we can't even do this. Okay. So what do we have to do here? The hint is this is from chapter 6, so you should all be able to do this. All right, so I can do normal CDF, but let me show you the steps. The first step is we're talking about an X because we're looking at a single stock, and that's just X because that's the variable you use to picking a variable. And we're assuming it's normal, so I'm going to write N, and then I'm going to have a mean of 12 and a standard deviation of 24. Any questions on that? So that's step 1. Okay, by the way, here's a guarantee for you. For your midterm, not this week's exam, but the midterm where most of the points are, and final, you're going to have to do something where you have to do each of those steps that I'm showing you. So write this down. Promise me, you'll pay attention. Okay, so X tilde N, 12, 24. That means X is normally distributed. Mean 12, standard deviation 24. The next step is to draw a picture. Not too fancy, but you should know that we get a normal distribution. And the mean is over at 12. All right, what does it mean if we lost money? Negative 12? Not necessarily. I mean, we lose money if it's negative 12, but there's more possibilities of just negative 12 for losing money. What does it mean if we lost money? Any thoughts? Okay, losing money means that your return is under 0. Is that clear? So the picture I'm drawing is the area of this graph to the left of 0, because losing money means you have a negative amount of money that you gained. Any questions on that? Is that totally clear? Okay, now we're ready for the normal CDF, but we needed to do the first 2 steps. So let's go ahead, and I'm just going to type it in, normal CDF, and we're going to have negative a bunch of 9s, comma, zero, comma, 12, comma, 24. Any questions on that? Okay, put in your calculator. Maybe I'll do that with you guys. That's how you want it if you're, it's not about wanting. You never want to lose money, but these are the steps to do to show what losing money is. Losing money means less than 0, right? You gained less than $0 means you lost money. And no, I never want to lose money, but you know, it happens sometimes. Not too often for me. I'm pretty good at the market. So I'm going to go normal CDF. This is the newer style. You might have the older style. So I'm going to go negative, bunch of 9s. And then the upper bound is going to be 0. The mu was 12. and the standard deviation is 24. Okay, so there's about a 31% chance of losing money. I'm not sure if that's what you expected, but that's what it is. So is this a good investment? What do you think? Okay, it's a trick question. The answer is maybe. It all depends. So let me tell you how I invest. I have some money that I call my play money or my fun money. And I want to make a lot of money, but if I lose money, it's not the end of the world for me. It's not like my retirement account, where if I lost all my money in my retirement account, then my whole life is going to suck when I get old, right? But if I put a little bit of money in and I lose, it's not that big a deal. Does that make sense? Please tell us the stocks you invest in. What I do, and it's over now, but it was really good when Trump was tweeting a lot about China, is I was playing the tweet on NVIDIA stock. So that's a long story, and I can't get into the details because it takes too long. But I made many thousands of dollars for a while. And I've made money in lots of different stocks. Okay, so again, that's my play money stock. Okay, it's just what you do, and I can make a lot of money that way, but it's risky. Let me show you another possibility. And this is really important in terms of not necessarily this class, but life, like how you can make money. Because hopefully when you're done with college, you'll have a good job. Maybe you have one already, and then you'll be able to invest, and then you'll make money instead of lose money or make nothing. By the way, if you put it in the bank, like say US Bank or Bank of America or something like that, then what's the mean? What's the mean if you put it in the bank? It's not zero. You get interest. Does that make sense? Right? If you put it in a savings account, then you get interest. And the mean is? It's a little closer to 1. You get about 1% or so, right? Sound about right? Depending on the bank account. Okay, but what's the standard deviation if you put it in the bank? Anyone know? You should all know, actually. One? No, it's 0. If you put money in the bank, you know your exact returns, and you're going to get that at the end of the year, period. You're going to get your 1%. Is that clear? So if you know exactly what you're getting, it doesn't vary. It's always going to be 1% if you put it in the bank. Okay? But 1% kind of sucks, doesn't it? 9%, 12% is a whole lot better. But again, if you have a standard deviation of 0, you have a 0% chance of losing money, but you're not going to gain much money either. Okay? Now let me show you another thing you can do. And this is really important in terms of life. All right. Let's look at the Dow. Do you know what the Dow is? You've heard of the Dow Jones, I bet. I'm hoping you've all heard of it, right? Okay, what the Dow is a bunch of stocks. Okay? And what you can invest in, and I have some money in this is not my play money. This is my safe money, and we'll see why in a bit, is you can invest in what's called a Dow index fund. Okay? Now, who knows how many stocks are in the Dow Jones? Anyone know? We'll see if any of you know investment real well. Okay, a lot? Yeah, that's true, but 30 it turns out. So if you invest in the Dow Index Fund, what you are doing is you are taking a sample of 30 stocks. Is that clear? Now we're going to make an assumption that's not quite correct, but I have to do it for this class. And we're going to assume that the stocks are independent of each other. Not quite correct, but if you do it long term, then you're pretty good. Okay, so now the question is, now let's go ahead and go back to the question screen. Let's see a good color for this one. Orange, maybe. Okay, if you invest in the Dow, and I'm going to remind you 30 index fund, what is the probability of losing money? Any questions on the question? Okay, it's very similar, but it's not the same answer. Remember, we got, for the first one, let me write it down, that was about a 31% chance of losing money for the first question if it was a single stock. So 0.31 was the answer. All right, well, the first thing is we don't have an X anymore. Now we have an X bar because now we're talking about the mean of 30 stocks. Is that clear? So now what we're going to do is we can write down X bar instead of X. Makes a big difference. And then we can say tilde n. Well, according to the central limit theorem, the mean is the same. Mu sub X bar is mu. So that's going to be 12. The standard deviation is not the same. Do anyone remember how to get the standard deviation of averages or of means? And that was the central limit theorem, and the hint is it's sitting there on the screen for you. Right? We take the standard deviation, divide by the square root of n. So that's the standard deviation, which is 24. Over the square root of 30. Okay. Notice, by the way, since I didn't mention, I wanted to mention, I forgot to. For the question that we just did, the normal assumption was necessary. So the assumption that it was normal, we actually needed and we used. So I want to highlight a few things that's important. And what I'm going to highlight is right there. What's that say? Yeah, exactly. So I don't know if you heard before, the definition of assumption means you're making an ass of you and me. That's assume. So assumption means it's just not necessarily right at all. Does that make sense? On the other hand, if we have 30, 30 is not quite more than 30, but I'm going to live with it and go with it. So if you have more than 30, you don't have to make this assumption. And that's much better, by the way. So just a note, that's really important. Now I can draw the picture. It's exactly the same picture, actually. Except the mean was still 12, but 0 is now far away because the standard deviation is so big. Any questions on that? So now we can go and we're going to do the same thing, but now our standard deviation is 24 over root 30. So let's go to our calculator and let's do our normal CDF. We're using 0 because it's the probability of losing. You win money if you get more than $0. You lose money if you get negative amount of money. Does that make sense, Pusha? So losing means negative money. Yeah, it's the same question. I rewrote it. If you invest in a Dow, what's the probability of losing money? Okay. The only difference is the standard deviation now changed. Okay, because now it's a standard error instead of the standard deviation. So let me go and share my calculator. All right, so here's the calculator again. I'm going to go back to the distribution, back to normal CDF. Our lower and upper are the same. Our mean is the same, but our standard deviation now is going to be 24, and then divided by, and then square root of 30. And let's hit enter. Notice what the probability is now. Has it changed? Okay, if you look at it, it's very different. Okay, so now we're looking at almost no chance of losing money. Okay, any questions on that? There is an assumption you have to make, and it's not perfect for the stock market, and that is that we're assuming that each of the items are independent of each other, which is not quite true for stock. Over long runs it is, but not over short runs. Okay, but now I don't know, any of you guys business majors or business type majors? If you are, you're supposed to know. Ah, David, then you better know. If you want independence, what do you call that in business or economics? What kind of investing is that? There's a word for it. It starts with a D. That's a hint. Okay, diversified investment. Have you heard of that, David? Haven't heard that before? Okay, so if you have what's called a diversified investment, then you have independence, and then these numbers really work. Whereas if you invest all in the same type of stock, if one's going up, the other's probably going to go up. But if you invest in different things that are diversified and independent, and we learned about independence in chapter 3. So if you have independent samples, okay, if your items in the sample are independent, then this works. Any questions on that? Okay, yeah, so this is a lot better than the bank. And if you're worried about losing money, this is a lot better than an individual stock. And again, these are index funds, and if you do a diversified index fund, that's even better, where it does some international stocks, it does some real estate, it does regular stock, it does all kinds of different things. You're going to have a high return, but a low probability of losing money. You're not going to become a millionaire with an investment of $5,000 though, because you won't win a huge amount of money, but you'll win pretty close to 12%. And that's a whole lot better than 1%. Do y'all agree? Okay, any questions? Any questions on this idea? I love this chapter because it's really useful for money. And I've been investing all my life, by the way, and I've done very well. I'm not a billionaire because I don't try to be a billionaire, but when I try, with my fund money, I usually make around average about 90 to 150%, which of course is really good. But again, you have to really work hard at it. Yeah, but again, it's all math. So I do make good money when I work hard at it, but it's a lot of work. So I should have invested a lot. I knew it was happening. I invested in overreactions. And for example, I've been watching the Chinese virus that's happening, coronavirus. Stock market overreacted and now it's back up. And that always happens. So if you want to make money, you look for overreactions. That's just a hint. Okay, but that's not statistics, but I figured I'd tell you my secret. Okay, it always works. Okay, so now let's go ahead and do another example that is big. What was the biggest thing in the news last night and especially today? It was supposed to be big last night and it didn't happen, but it happened today. What's the biggest thing in the news? Any of you paying attention? A, I guess not. Impeachment, no, it wasn't number one actually, because impeachment didn't happen today. That happened last week, and then it's going to happen again later this week or next week. All right, let me pop it in because all of you are stuck. Again, maybe you haven't been watching the news. Yeah, Iowa, there we go. Okay. So the biggest thing in the news was Iowa. Now, Iowa's over. It was supposed to be over last night, and that was the big in the news is that they totally screwed up, and they found out today. So what I want to do next is we're going to look at a poll. And what we've got is the next place is New Hampshire. I'm not sure if y'all know that. Oh, by the way, if you don't know about Iowa, Iowa was where the first primary election happened. Happened yesterday. They were supposed to announce it yesterday, and they screwed up, and they couldn't announce it until this afternoon. Stuff happens. So the next polling place is New Hampshire. And by the way, if you want to say, if you want to know who won in Iowa, by the way, anyone pay attention to the news? Caledon, you might, because you actually knew it was Iowa at least. Oh, no, we do know. No, it wasn't Bernie, actually. Yeah, well, Trump won but everyone knew Trump was going to win the Republican. That wasn't big news. Okay. Yeah, it was Pete Buttigieg. If I pronounce his name wrong, I apologize. But if you look at the polling, here's the question. I want to look at the last poll. And the question is, what we've got here is Bernie Sanders has a commanding lead in the Granite State. That's New Hampshire, at 32% support. Okay? And if you look at the next two, they're at 13% and 13%. That's Biden and Elizabeth Warren. So now, if this is a representative sample, is Sanders going to win this one? And I'm going to make an assumption. I'm going to make an assumption that 26% of New Hampshire voters are going to vote for Biden and Warren. And we want to say, is Sanders going to do better than the combined Sanders and Warren? Does that make sense? Any questions on the question? Okay, so now I'm going to get back to my writing screen. Again, what I like about this particular topic, this particular chapter, is I can always bring in cool stuff. And this is one of those. So let's do it. Let me go and select. I got to get rid of what we had because we're on a new piece of the central limit theorem. So let's look at the central limit theorem. Okay, so the last one was the central limit theorem for means. Now we're going to look at the central limit theorem for proportions. So the first thing is, if we look at our symbols, we have some new symbols now. So one of them is we're not going to be looking at mu sub x bar anymore. We're going to look at mu sub p hat. Okay, and I'm not sure if I mentioned it when we did means. We use Greek letters, right? Like mu and sigma. That you know, right? Anyone know why we don't use Greek letters for proportions? When I started teaching about 25 years ago, they used Greek letters, but it was way too confusing. Anyone know why? Anyone know what the Greek letter for P is? Okay, you all know it. Okay, the Greek letter for P is pi. And that's just way too confusing to start calling pi a proportion when it's 3.14, etc. Do you agree? So it has become standard in the last 20 years or so to use p hat for the sample proportion and p for the population proportion. So mu sub p hat is the mean of all possible sample proportions. And the theorem, the central limit theorem, says that mu sub p hat is very simple, just like the central limit theorem for means. It's what you expect is equal to p. So the mean of the sampling distribution for proportions is just the population proportion. And we can also write, and this one's not as obvious, but let me write it anyway. And that is sigma sub p hat is equal to the square root of p q over n. So in particular, let me write this down because I don't know if I've used q before, but we're using it now. So q is equal to 1 minus p. So notice p is a proportion of people who said yes. So q will be the proportion of people who said no. Any questions on that? Okay, now this is really important because this is a place where so many people screw up, and you don't want to screw up. And that is 30 is not the number for having a normal distribution. Can you remember that? Because I will let you know, usually around 60% of the people don't get it right. So don't be one of those 60%. Be the ones that get it right. And that says that if NP and NQ are both larger than 5, then the distribution, the sampling distribution, is approximately normal. And that's the central limit theorem for proportions. Any questions about what this says? Any questions? Okay, so now I have a question. And we have to go back to the article to see, is that, remember we said that the other two had a combined NP. So N is a sample size, and P is the proportion of people that say yes. Sometimes we call that the proportion of successes. It doesn't always have to be people. You know, it could be some experiment on dogs, and you could say a proportion of dogs that, I don't know, that dogs that shook your hand when you asked them to shake or something like that. So NP is the total number of people who said yes, because that's what happens if you multiply by N, and NQ is the total number of people who said no. Yeah, exactly, or didn't agree if you like that. Okay, any questions so far? Okay, I need to go back because not that one. I want to go to that one. Oh, you can't see this, but I want to remind you that the combined for Biden and Warren was 13%. So that's important. So what I want to say is that if Sanders has, I guess, 26% support, and you surveyed, and I will just have to tell you, but I'll show you in a bit, 500 randomly selected voters. What is the probability that at least, and what Sanders got in the polling that happened in the Emerson polling was 32%. At least 32% of the voters, of these voters. Any questions on the question? Okay, I think I should reshare my desktop so you can actually share the news article so you can see it. So you can see where all these numbers are coming from. So here's the polling. So notice that Sanders got, at least in the poll, 32%. So we want to say, well, was that just random chance that maybe it was just these 500 randomly selected voters and we just really didn't get the 26% because they just happened to like him? Or is it too unlikely that it was random chance and we're going to give up the random chance idea? Okay, and it tells us N is 500. Any questions on that? So that's where all these numbers are coming from. So now I can go back to the question. So again, now we're going to do our 4 things. The first is we can say p hat, because that's our variable now. Tilde, so it has a distribution of normal with mean. So remember, the mean is your p, and we're assuming it's 0.26. And the standard deviation will be the square root of 0.26 times 1 minus 0.26 is 0.74. Divided by 500. Any questions on that? Okay, then we can draw our picture. There's our picture. We have 0.26. And we want to find out what's the likelihood of getting at least 0.32. So here's 0.32, which is bigger than 0.26. And we want to find that area. Any questions? Any questions on that? All right, so now I'm going to go to my calculator and we can actually find this. So now let's do that. So if I go to my calculator and I'm going to go second distribution, then I'm going to go to normal CDF. My lower was 0.32. The upper, just throw a bunch of 9s in, because it goes on forever. Our mean was 0.26. And our standard deviation now is going to be the square root, second square root, of 0.26 times 0.74 divided by 500. And that parenthesis. Any questions on this? I hit enter. Enter again. And notice, is that a high probability or a low probability? Yeah, it's a low probability. So you're going to say, well, maybe if it's such a low probability, that maybe Sanders has more than 26%. Does that make sense? Because that was our assumption. We're assuming Sanders had 26% of the New Hampshire vote. Then they did the sample, he got 32. Now we're going to say, well, he probably has more than 26. And yeah, Sanders is going to win. Any questions on that? Okay, that's how statistics works. That's the whole point of the central limit theorem, to be able to make conclusions like that. Okay, now again, we've got some assumptions. One is that it was a unbiased survey. That's always an assumption. It was an unbiased survey. And another is that nothing's going to change since that survey to next week. And given what happened today, things could change. Buttigieg might actually get a whole lot more because people say, say, hey, Buttigieg's a winner. People like to vote for the winner. But that's some other things. Any questions at all on this example? Any questions so far? Okay, let me go back. Okay, was the distribution large enough to use the normal? Was the sample size large enough to use the normal distribution? How do we find out? What do we look for to find out if we were able to use the normal distribution? The hint is it's in red. It's up there on the screen. Yeah, NP and NQ have to be bigger than 5. Well, let's calculate them. NP is equal to, well, N was 500 times P. P was 0.26. And if you calculate that, that's 130. Any questions on that so far? NQ is equal to 500 times, and now we're going to multiply that by 0.74. And that is 370. If I did everything in my head right. Okay, what can we say? Yeah, so N was 500. Hopefully you understand how I got that, because that was given. And the 0.74 is 1 minus 0.26. And that, again, you can put in your calculator. You don't have to do it in your head like I do. You're allowed to use your calculator. So there's 26% that say yes, then 74% say no. Yeah, it's definitely 130 and 370 are much bigger than 5. So there's no issue here. So that means that the sample size was large enough to use the normal distribution. for this calculation. Any questions on that? Okay, I want to mention something that's pretty important, and that is that you're going to be responsible for doing something very similar to what I just showed you right here on the screen for your discussion post this week. So this is one of the harder discussion posts, just a warning, because you're going to have to do all this detail stuff. Okay, and some people get confused, and you're happy to post on the Q&A forum if you have any questions about it. I'm always happy to help you out. But again, you're expected to look at my model post. I did something very similar to what you're seeing right here. Okay, any questions on this so far? Okay, let me do one more example. I think it's worth it. And I think I'll do it. I think we got time. I'm going to spend a little more time than I thought I was going to spend because I want to do that third type. So let me go and get rid of this. Okay, central limit theorem. Or sums. Okay, first thing, anyone remember the symbol for sum in math? If you're adding a bunch of things up, not just one thing, but many things. The hint is you're not going to be able to type it in the chat box because it's a symbol that is not, you know, your standard English symbol. You remember it? Good, good, Caledon, you remember. It looks like an E, okay? And it's as confusing as can be. Sorry, don't shoot the messenger. So let me draw it for first thing. We're gonna be looking at mu, population mean of all possible sums. Okay, yeah, it looks like a triangle E, so what I wrote. And unfortunately, this is the Greek letter sigma, but it's capital, whereas the other sigma is lowercase. Just like English, we have different capital and lowercase letters. So it's mu sub capital sigma is equal to, turns out it's not mu, which makes sense, because if you looked at 100 people, let's say you wanted to ask how old they are, and you added up their ages, you don't expect it to be the average age. Going to be, you know, if you add them up, you get a big number. So it turns out it's n mu. So you take the average age, multiply by how many people, that's the average sum. Not too unexpected. And sigma, lowercase sigma, sub capital sigma, sorry, which is the standard deviation or the standard error for sums, is now going to be equal to sigma, lowercase sigma, times the square root of n. Any questions on this? And let me just type in n greater than 30 gives normality. Any questions on the central limit theorem for sums? Okay, and honestly, all we're doing here is multiply by n, right? Multiply mu by n, you get n mu. If you take sigma over root n times n, it turns out you get sigma times root n. Okay, so let me give you an example. I'm not going to bring in a current event because I don't want to spend a lot more time today because we're almost out. I always want to be done before 7:30. Okay, suppose the mean amount of money people spend in the snowboard snowboard rental, snowboard, let's call it ski, and snowboard shop. We're in Tahoe, or I'm in Tahoe at least, so that's our big thing is ski and snowboard shops. Okay, let's say, I'm just making this up, let's say it's $54 with a standard deviation of $41. Some people spend a lot of money, some people don't buy anything. Okay. So now the question is, find the first quartile for the total amount of money a group of 40, let's go 30 actually, let's go 60 customers will spend. Well, if you think about it in business, you care a lot more about the total amount of money you're making in your store than the average amount per person. Because the total amount of money is how much money you get in your cash register at the end of the day. Hopefully you agree with that. So this one makes sense to think about sums instead of averages. All right, so now I'm going to go ahead and let's write this out. So we could say mu, oh, sorry, not mu. Let's go sigma tilde. So sigma has a distribution. The sum is normally distributed. And by the way, when you're talking about means, when you're talking about quantitative data, even if it's about sums, still over 30 is what you need for normal, as we see. So we're good with 60 customers. We don't have to make the assumption. But normal distribution. And now what we can do is we can say that the mean now is going to be 54 times 60. Which is what? 3240, if I did my head right. And the standard deviation is going to be 41 times the square root of 60. Which, that's hard to do in my head, somewhere around 320. Okay. Any questions on that so far? Okay, now I draw my picture. Remember, there's 4 parts. So I'm going to draw my picture. And you're used to this picture by now. It's always a normal distribution. And our mean now, again, 54 times 60 is 3240. Okay, I want the first quartile. Who remembers what that means? What does it mean to be the first quartile? Yeah, it means the area, not the x value, but the area is 0.25. Right? Most of you did this on your discussion post that you had to do. Okay, from last week. Any questions on that? We want to find this value of x, which is the first quartile. So do you remember in your calculator, what are we going to have to use this time? Yeah, this is going to be inverse norm. So let's do it. So I'm going to go to the calculator. And now I'm going to go to second distribution. That's like the thing we're doing in this chapter. Inv norm. Area is 0.25. The mean was 54 times 60. The standard deviation was 41 times root 60. And left is fine. Your calculator probably won't have that word, so I ignore it. I hit enter and enter again. So now what we say is that the first quartile is $3,025.79 if you want to do dollars and cents. Any questions on this example? Okay, and finally, for this example, notice that n is equal to 60, and 60 is definitely greater than 30. So the normal distribution, so the normal assumption was not needed. Remember, assumptions are bad, but we don't have to assume. Okay? We don't have to make the assumption because the central limit theorem tells us that we have a normal distribution. So no assumption needed. Any questions on that? Okay, finally, secret word time. Okay, this is, so we don't have to use a normal CDF. Yeah, it's not we don't have to use a normal CDF. You can't use a normal CDF because we're going backwards. We're given an area. We're looking for a value of x. So that means inverse norm. Okay, very important to practice to know both types because you will be tested on this. Okay, so the secret word. This is one of the few times in the entire class where there is no secret word because it's a secret number, it's 5. So the secret word is 5. Why 5? Anyone know? Anyone know why it's 5? 5 more weeks? No, we have a lot more than 5 more weeks. We're in week 5, but that's not it. No. I know it's been a half an hour because if you have a yes/no survey question and you want to find out if you have a large enough distribution, NP and NQ have to be greater than 5. Remember that? Yeah. So the bigger than 5 for the assumption. That's the reason. So don't forget that number because everyone writes 30. Don't write 30 if it's a yes/no question. 5 is the important number for yes/no questions. Any questions? I think I'm going to kill the share. So are there any questions at all about anything we did or anything that's coming up? Remember that test. Make sure you spend some, give yourself enough time to take it. And don't hit submit until you're all done with all the problems. And then you can go back and do more, as long as you don't submit the whole thing. Okay, you could do each individual question, but I think on the bottom there's a submit button. Don't hit that submit button until you're ready to say, I'm done. Yeah, it's okay. It's just a number. It's not the word. Okay. Any other questions? David says you raised your hand. I'm not sure. You're not typing anything.
No, I was just wondering, like, can you like start the test and then log off like the homework and come back, or do you have to do it all at one shot?
Yeah, that's what I was just saying. You can do it. I believe, but I'm not sure, there's a submit button on the bottom. Don't hit that submit button on the bottom of the whole thing until you're ready to say I'm done. If there isn't a submit button, then don't worry about it. It's hard because I'm not a student, so I don't get to see what it looks like as much. I have a little bit, but not all the view. So then you should be fine. So you do the problems, and then you can go and come back to do more problems, because it is a long test. And it's a good review for, you know, everything we've been doing. Yeah, so when in doubt, carry a lot of decimals. If it doesn't tell you how many, just carry a bunch. Usually 5 or 6 is just fine. And that's not just for the test, that's for all the homeworks too. Okay, for the written exam, that's different because I grade it, you know, personally, and that's different. But for the one that you have to do this week, then just keep a bunch of decimals unless it tells you round to the whole number or something like that. But read the question very carefully and make sure you answer it the way they want it answered. It turns out that most of these questions I didn't write, but the questions from now on, I wrote most of them. I had a team, and I kind of led the team. I think I did chapter 5, if I remember right, but the others were done by other people. Okay, and they're used by literally 100,000 people now, 100,000 students. So the good news, there shouldn't be, you know, any errors left because all these people let me know if there's any mistakes. So when you're saying off by one number, if they want to, if they ask you for a question and it's got a long decimal, just keep a bunch of decimal places and then you'll be fine. But if you're off by a number, if it was 7.35 and you write 9.35, that's not okay. Does that make sense? So I'm not sure if that's what you were asking. So it depends on the number. That may be wrong, actually. So if the answer is 0.35 and you do 0.34, that might be counted as wrong. But if the answer is 0.3592537 and you do 0.3592538, then you're probably okay because it's so many decimals out. But 2 decimals is usually not enough. So I would go at least 5 or 6 if it doesn't say. It doesn't take long to type the numbers in. And you use calculator for sure, or computer, to get your numbers. Any other questions? As always, I'm always happy to answer questions until you don't have any questions left. And let you know that, you know, tomorrow and the next day I'll work more on grading your projects. Again, I'm about halfway through right now. And then I'll grade the other half the next couple of days. It takes a while to grade. They're worth a lot more points, so I take it a lot more seriously in terms of comments and stuff like that. And also make sure, and I put a note in it, but make sure that you share my comments on your paper with your partners if you're the one that submitted it, so that they can see the comments too. Because only you can see the comments in Canvas, so you have to share what happened. Okay, other questions? Again, if you don't have questions, we can say goodnight, but if you do, I'll be happy to answer. Okay, you two have a good night, Conan. Have a good night, Kate. Hope you do more. I try to vary my examples so it's not always stock. But the stock's a good one for this week. Not everyone's in business. There's health people and psychology people, etc. Political science. All right, have a good night, David. Any other questions, Mark or Shane? Okay, if there's no questions, then I'll say good night. And don't forget to post on the Q&A forum any questions you might have, and I'll be happy to help. So until next week, good night.